So welcome to webinar 1 on tricky topics and misconceptions in geometry. We're going to be starting with a tiny little bit of Pythagoras, quite a bit looking at area and volume, and some bits on vectors. So very much just leading up to GCSE level. Now, this all looks quite busy because there's so much geometry in the GCSE curriculum. I couldn't put it on to, I don't know why I did it like this, considering I've made it like this. I was struggling to drag this onto the next slide. It was really difficult. And we're definitely not going to look at all this today. We will look at some of it next time. Well, not necessarily next time, but on another day. So there's all the properties of angles, and then the definitions and properties of all the different shapes, all the different equilaterals and triangles and language. The things about constructing triangles, and then applying all those angle facts in order to derive various things, including Pythagoras' theorem. And then there's lots to do with circles and circle theorems, and just so much language. There's so many different things to learn, and the students, kite, rhombus, just the very basic shapes before you even get into three-dimensional, they really struggle with it. And they've been learning these since primary school with all of these different words. But, it's our job just to try and find ways to make them really stick, because they do get confused. And often part of the problem is that we teach it all as one big lump together. So then they're faced with all of these different words all at once and they get very confused. Now that can be really useful in terms of, what's the same and what's the different. Can you remember which one, identify which are which, but can also cause them to just get stuck, something stuck in their mind of what it was. So then units of measure, they're expected to measure and draw scale drawings, and no formulae, quite a lot of formulae, all the areas and perimeters and that sort of thing. So there's lots going on, and there is a lot to geometry in terms of reasoning. And I observed an excellent lesson a couple of weeks ago where the teacher had just basically gone into the cupboard, and if you have hopefully got a resource, a maths resource cupboard at your schools, to go in and have a bit of an explore, and there's all these, you'll find the weirdest things, all these different, shapes and three-dimensional shapes and things that just look like playing around and don't often lead to necessarily some particular lesson or particular topic that you want to teach. And so there doesn't necessarily seem a point to them or a need for them. It's just a bit of playing. But in this lesson, she had just basically left them to play, which is she'd put different resources around the room and just said, have a go, just do them. And some of them were just, having those different shapes like you get in a cracker toy where you have to make it into a square. And others, she had those hexagons and those things that you can click together to make different three-dimensional shapes. And just, little cubes that they could play around with. Just all sorts of what looked like toys that actually, when the students start to play with them, they think they're just playing, and then they start to realise that actually, well, they may not appreciate this themselves, but the teacher can see that they're having to question certain things about, well, this doesn't fit here, so what can I do instead? And it's just bringing up those sort of questions that develops their reasoning abilities, so that in an exam, when faced with just a question, they can start to use that reasoning that they've developed elsewhere in order to think, well, what should I do next? You know, and they get to a point where perhaps they've got stuck with the, you know, with the geometric thing they were playing with. And at that point, they then ask the teacher for help, and that really enables deeper learning, because they've reached a point where they've tried it themselves and they've struggled a bit, and they're really open to sort of what the teacher has to say, rather than standing at the front of the class telling them something that they didn't feel that they particularly needed to know at that point. So providing them with the knowledge at the point at which they're stuck can be very valuable. That was just my sort of reflection on quite a good lesson. And to not dismiss all the random stuff that's in the cupboard, often just get it out and have a play. It can seem a bit scary having open-ended tasks where there doesn't seem to be a particular objective. But I think developing reasoning abilities now with the new GCSE syllabus and the way that the curriculum has gone and mastery, the benefit is that you can probably get away with on a lesson plan saying that what you are trying to achieve in a lesson is just developing reasoning. It doesn't have to be a particular topic-based result. Speaking of which, when I see you in February, I was going to do an afternoon session on decision maths, which sadly has been removed from the new syllabus going forward to A-level. So instead of that, I'm going to do a whole afternoon of problem solving. So we'll look at how to use open-ended tasks to get the students more into developing their problem solving and their reasoning. So, a little bit of a starter review. This can be a nice one for either, you know, a class that's done Pythagoras' theorem and you feel that they could develop, you're trying to develop it into algebra, or for a top class that's never seen Pythagoras before, quite unusual, but you know, maybe lower down the school. And my recommendation would be to mention to them that perhaps they might like to call the long edge of the square C, sorry, the side of one of the sides of the square C, and you probably wouldn't put a bit in saying what they were doing necessarily. So they didn't actually know where they were going, and suggest instead that can they find a relationship between A, B, and C, which is what I want you to do now. Now, in fact, as you can see, you are going to be proving Pythagoras' theorem. But I want you to use this representation to prove Pythagoras' theorem. Is that all right? Do you understand what I want you to do?
Yeah, I think so. To be honest, this is probably the only theorem that's stuck in my head. Actually, is it's a way of summing up the area of the large one with the sum of all the others, and you end up hopefully with the Pythagoras' theorem at the end.
Yeah, yeah. So I think that's it. The benefit that you have of knowing that you're thinking about areas, which hopefully the students will get to. And this is quite a nice one, actually, if you've just taught area, to lead on from in order to prove Pythagoras' theorem. So often we just teach Pythagoras' theorem by saying, okay, it's this. Now go away and practice it lots of times. But if they develop this themselves, hopefully they'll have a greater depth of understanding. So yes, so think about areas of triangles and squares and using the letters that you've got there. Please try and get a proof. Robert, do you want to mute yourself? That's making a weird noise.
There we go.
There you go. So have a go at doing that. Please feel free to either, well, unmute yourselves and talk, or you can have the question bit, or put your hand up when you've done it. Must be really my typing, my writing in mouse takes absolutely ages. So complete the hints and everything. So Robert, what have you come up with as the formula that you come up with at the end?
First thing was the area of the large square being a plus b times a plus b, and that just multiplies out a squared plus 2ab plus b squared.
Yep. Yep. So that was the area of the square. Yep.
Yep. And then add up the areas of all the 5 different shapes inside individually. C squared obviously being large square.
Yeah.
The area of the triangle, a half a times b. 4 of them, and then add all them up, so you'll get c squared plus 2ab.
Yeah.
Then obviously both sides will equal one another, the large square and the sum of the internal shapes. And 2ab will cancel from each side, leaving you just a squared plus b squared equals c squared.
Yeah. Good. Wayne, how was that?
Yeah, it was fine. As soon as you put on the area of the triangle, and I thought about that, and obviously 4 of them. Yep, and as Robert said, 2 sides are just equal, and the 2ab disappears. So, yeah.
I think, well, Robert was particularly fast. You would expect the kids to take quite possibly, well, at least 20 minutes to do this sort of thing, depending on where you're coming from and you know how many hints and the type of class. Can you see? Do you have any ideas when you might like to use this?
I guess as you say, when you're introducing Pythagoras, then it'd be quite a good idea to build it into a scenario then.
Yeah, have you guys done any, seen any lessons of teaching Pythagoras or geometry so far?
I haven't yet. I've been doing a couple little bits of algebra, and actually I got my first full lesson yesterday,
Okay.
which went reasonably well. I'm still here and smiling. But geometry is a little bit later on in our syllabus.
Right. So they start with algebra before geometry?
Yes, they've been doing pretty much up till now. They've been doing number theory.
Yeah.
And then yesterday I just started them off on sequences.
Oh,
So they'll have a couple of months of that, and geometry will come later on.
Yeah.
I think they wanted to get the algebra first before they start dealing with geometry, otherwise it'll just get messy.
Yeah, absolutely. I mean, you can see why, because when we're talking about formulae for everything, it obviously involves letters, so yeah, they do need that. But I have seen it done the other way though, where they come at it fully from geometry, and then kind of there's this need, the students feel a need that they're missing something that they didn't really have, and that was the sort of knowledge they needed to be able to manipulate and use these. But either way, I think it is more difficult to do it the way you think so. And Wayne, have you seen any geometry?
Only geometry really has been with kind of polygons, that type of thing. So exterior angles, interior angles, and things like that.
Yes, because again, the angles.
If that comes under geometry.
It does. Yeah. Yeah. And I guess the thing is that again, the angles are more accessible because they are still numbers. Really, you haven't yet got to a point where they necessarily need algebra. They don't have to define it using algebra. Good. Anyway, so that's just a nice little sort to show you. And another nice thing, do either of you know what a Pythagorean triple? Have you come across Pythagorean triples?
No.
I've known they existed. It's where Pythagoras, the numbers involved to come out as whole numbers, like as you can see there, the 3, 4, 5, 5, 12, 13, and so on.
Yeah.
I'm sure there is probably a formula for them to work them out, but I'm not sure about that one myself.
No, and I'm not either. I think there is for certain things, like whether it's odd number or something, but on this Blogspot, you can always go and have a look. She's a bit obsessed with Pythagorean triples and has got all sorts of things. And again, it's one of those things that you can set the kids off to investigate. It doesn't in itself have, again, like much of the things, you know, when the kids will say, why are we doing this? It doesn't have an immediate usage, but it's very useful for them if they can spot a 3, 4, 5 triangle. So if it's just scaled up so that, say, everything was just, you know, a multiplied by 4. So they had a 12, 16, 20 triangle. They could somehow spot what the final length was without having to do the whole of Pythagoras, because they recognise these types. But it's just something to play around with. Getting onto some areas, I have taught students who struggle all the way to the failure, unfortunately, of their GCSEs with knowing just the area of a square. But hopefully the majority of students manage to grasp that and how to find the area of a rectangle. And then it's a nice little way to show them that when you have a parallelogram, you can either get them to split it into triangles, but I quite like to show them just this little slide as it shows them moving it around to make basically the same area as that of a rectangle, where the area is the base, it's still got the same base, multiplied by the vertical height. In the exam, they, a bit further on in GCSE, they would be deliberately mean and give them this side so that they then have to somehow use Pythagoras. So they might give them one bit of the triangle and split them so that they have to use Pythagoras to find the straight edge or something like that. But generally it's just a systematic bit to show them that visually the area of the parallelogram is still the same as the area of the rectangle. Altitude, I don't think I very regularly use that word at all, if ever, to describe the vertical height. Because I tend to just say the perpendicular height of vertical height. But yes, so that's hopefully a way to get them avoiding using this length, which is the deliberate pitfall that the exam will try to track. Trapezium, the area of a trapezium, the reason that I've just put this on is because it used to be given at the front of the GCSE exam as one of the key formulae. However, now it is not. They're expected to know it, and it's not particularly difficult. They can think of it as finding the average of the parallel sides and multiplying by the distance between them. Or in algebra, if we write it, it's half of A plus B times H. Again, with trapeziums, they get a bit confused, and this is all to do with invariance and the fact that students struggle if you don't draw a triangle with its base on the bottom. They have the same issues with trapezium. If you draw it so that it looks slightly different, they then get confused about what type of shape it is. And I think that's the main thing with trapezia. There's so many different ways that it could look. So as long as they can spot that there are, and obviously my picture's not brilliant, but there are parallel sides, they can label the parallel sides A and B. And then again, like we have with the parallelogram, we don't care about any of the sloping sides. We just want to know the distance between, which is why it's quite useful to call it the distance apart, so that they can identify that H is this direct distance, is perpendicular distance to the parallel lines. This might seem very straightforward, but these are just little things that the students really struggle, and when you start teaching them, so things that you're like, oh well, look, it's the parallel side times by this length, and if you draw it like this and you show them like this, then to them they're thinking, oh, it's the length of this side, and then they're confused about, well, if it's length, why is it not the length of this side? Which side do I choose? So calling it the distance apart can just help, or talking about parallel and perpendicular distances of what you're looking for. Now, interestingly, I was reading a book to my daughter last night, which is a book of many questions that young children ask. They've been answered by lots of people. And there is a particular one that we got to, which was, which shape has the most sides? And it had been answered, they've got famous people to answer these questions. It had been answered by Marcus de Sautoy, and he had said the circle, because it has infinitely many sides. And that actually was used as a way of determining so what we call squaring the circle. The fact that it has lots and lots of sides, so you could technically break down a circle by drawing lines around it, so that it wasn't so much of a circle, and then make those lines smaller and smaller and many, so that they're so tiny that it is now becoming a circle. And it was Archimedes. I don't know why there's a BCE. But anyway, so that he was the one who basically came up with the idea of putting a square in a circle and working your way up from that. So if we look at a square in a circle, can you find the area of the square? Have a go now. Come up with your own way of labelling it in such a way that you can tell me the area of the square. And when you've done that, put your hand up, although Robert, your hand is still up from previously. So my hint would be that I'm looking for it to be, I think, best in terms of art, best type of things in art. Good. So Wayne, what have you got? So Wayne, what have you got for the area? Do you need to, are you talking about you need to unmute yourself?
Oh, sorry. Can you hear me now?
Yes, I can.
Just talking to myself.
Sorry, I thought suddenly, oh, hang on, he's probably just talking to himself. Yeah, sorry about that.
Okay. All right. Yeah, so I don't know if you heard any of that, but
No,
basically, obviously, work out one side of the square,
yeah.
which I got was r times root 2, and then r root 2 times itself basically gives you the area, and I got that as 2r squared.
I realise that I have done it wrong because I've forgotten to square root it. Oh yeah, so it's 2r squared. Yeah, sorry. Yeah. You know what I've done? I have fallen straight into the similar trap that the kids have done. And to get my area, I just multiplied by 2 instead of multiplying by the other length and squaring it. So that's why I'm wrong. But yes, you're absolutely right. So
Problems.
yeah, you know when you work something out and you think you go, yeah, that's strange, but you're right. So yes, the students often get a bit confused because they probably would have started with D, whereas obviously having it in terms of R is much more useful because then we can split it into each of the radii and find the length of this side of the square. And so the r squared plus r squared is c squared, and so the root of that is just the diagonal of the square, so what's the sum here? And then 2r squared rooted is just root 2r, and then the area just means you then multiply that back again to get 2r squared. Now technically, just by squaring and adding them together, you get c squared, which actually, as we know from what we were doing for the Pythagoras, is in fact the area of that square. But anyway, so that is the area of the circle if we put a big square in it, like the area of that square, 2r squared. So we're starting to get somewhere towards some sort of approximation for the area of the circle. What about if it's a hexagon? Have a go at doing this one. What would the area be of this hexagon? So I can get a little bit more complex now. Wayne, have you got that then? Because, do you know what? I have completely forgotten how to do this now, so I would definitely appreciate a hint.
Sorry, Sarah, say again?
Oh, how have you got
Did
on?
I get that one?
Yeah, have you got that one? Because
Well, what I did, well, yeah, correct me when I go wrong, but so we know, like before, we know
yeah,
R and R,
yeah,
so we can work out the outer length, which is again is 2r squared, the same as before.
so how did you get that? That's my question.
Is it not the same?
No,
Oh, no, cool.
no,
No, of course it isn't.
because it's not a right angled triangle.
Yeah.
Now
It must be yeah, no, sorry, that's complete, isn't it? Yeah.
no, do you know what? I was just looking at this exact thing going, I don't know what to do with this because I don't actually know how we're going to do this without using more complicated trick that I've not told you. Robert, have you got any ideas?
I'm just saying, I'm saying obviously here, hopefully, the small 6 triangles are bilateral from the
Yeah.
hexagon.
Yes,
So
because
each side of a
that
small
is,
triangle is length r.
so that should be R as well. Is that what you're saying?
Yeah, and then we could work out the height
Yeah.
of one of the smaller triangles in terms of r.
Yeah.
Work out that area of a small triangle and then multiply them by, what's that, 12?
Yeah. So yeah, so that's actually half. Yes.
So
Now,
that height would be something like r squared minus a half r squared over 2 or something.
so half base times height. So I've got quarter times r squared, and then I've got 12 of those. So I've got 3r squared, or if I just do, I shouldn't. Now, when I
Well, the
went,
height, sorry, there you go.
no, go on. What have I done wrong? Oh yes, no, sorry, that's r.
I was just thinking the height is the square root of
Yeah,
r squared minus a half
yeah,
r
you're right.
squared,
Yeah.
which will be a quarter r squared in total.
So
It starts to get quite messy then.
3/4 r squared times. Whoa. Right, I'm going to delete this. You know, when I wrote this slide, I could totally do this because I totally remembered that they were equilateral triangles and did that as R, and then bizarrely that's gone out of my head still. I my arrow back. Because I have actually written it. Yeah, there you go. They are.
They are equilaterals, aren't they? Because
Well, are they?
yeah, because the exterior angle is 30 degrees.
Well, there's
1,
360 in the middle, isn't there?
Yeah.
Divide it by 6, you get 60 degrees. On two sides are r. And the intermediate angle is 60.
So they must be. I'm just wondering what this. So that so they've split them. So they've just called this one R, and that's the root over 2 half base. Yeah, so half base times height. Let's just call that H. That's a half a base. Root 3 over R. Root 3 over 2R is what they've got for the height. And that's right, isn't it? Because I've written 3/4 R squared, and then we need to square root that to get that. Yeah. So then when that's all multiplied together, it ends up, when you do this, if you work it out roughly, about 2.59 R squared. So this development of this towards the area of the circle involves the knowledge, as you were talking about, the knowledge of polygons, Wayne, that you've been teaching at the moment. Sorry, Robert, can you just mute yourself? Thank you. So on a day when I'm not having a complete mental blank, this would still be very tricky for the students because, as you can see, you can just go not knowing at all what to do, and then you need the flash of inspiration to remember that these are equilaterals, and thus that is R. And then use reverse Pythagoras. So to do this, they would really need to know Pythagoras. And I'm not really sure that Pythagoras is ever taught before learning the area of a circle. But perhaps it should be, in order for them to get towards this. Anyway, the idea of this was that Archimedes kept finding shape, putting more and more triangles in, basically. And the area of each triangle was always the same as we had before. Before we had 6, and it was half times space times height. And then he's putting in n triangles, so n of those. And as that gets closer and closer and closer, what we find is that the h, the height that we've got of this triangle, gets closer and closer and closer to the actual radius of the circle. Whereupon you can say, okay, well, in that case, the h is actually the same as r. And 360 degrees in radians, which we will not do until probably next year, I think. We might do a bit of it this year. 360 degrees is the same as 2 pi, and that is where this 2 pi comes from. So that when we multiply that out, the 2's cancel with the half, and we end up with the area of the squared pi r squared. So this was the sort of the development towards finding the area of a circle. But what you would need to know, the class would need to know radians and be really adept at using Pythagoras to sort of develop this. So anyway, something more for us perhaps than for them. But actually, but actually higher GCSE could be something that they could engage with and link them into talking to them about radians. Just going on to talk about circumference, the kids find the language so difficult. And although, you know, they know that area is the shape, the space contained in the shape, I think they sort of say that to themselves, and they sort of know, okay, the area is the whole thing. The other one must just be going around it. And whether that's the word perimeter or circumference, they just seem to struggle with it. So often it's really useful if you can actually get them to figure it out themselves. There's a video of an Australian teacher getting his students to do this, where he's put lots of objects around the tables and sent them off with a ruler or measuring tape and asked them to complete a table that's got the name of the object, the diameter, and the measurement as they've measured around the outside of the circumference. So, of course, they're all measuring tapes in fact, to a round thing. And then he's asked them to measure at least 5 objects in the room and see if they can spot a relationship between the diameter and the circumference. And then sort of saying, oh, well, you might want to use a calculator to do some division and see what you get. And hopefully they'll sort of be like, oh, I'm getting roughly 3 when I divide them. There's some sort of relationship related to 3. They might get towards it being more precise, that it was always something close to 3.1, 3.14. And hopefully that would lead to a discussion about pi, as well as a discussion about rounding and the calculator button. But would get them to realise the relationship between the circumference being 2 pi r or pi d versus the area needing to be squared. Anyway, just moving on to talk about composite shapes and the area perimeter. Here is a nice little one for you to do. Something hopefully a bit easier than what we were just doing. Find the area and the perimeter of that shape, please. Well, you can leave it in terms of pi. I know, as I said, one decimal place. If you haven't got a calculator, then feel free to leave it in terms of pi. So try to find my calculator. If we hand it moved. Right, so, sorry then.
Eventually.
So, what did you get, well, Robert, what did you get for the area of the shape?
I got the area to be 226.2 metres square.
Oh, okay, I've got a different one, so let me see.
What I got wrong?
Well, no, it might not be you, believe me, I think I'm not quite with it still. Let us have a look. But, do you know, this is one
I
of those
got
things. What did you get, Wayne?
I got 64 plus 8 pi.
Yes. Ah,
Yeah.
it's 8 pi.
Oh, I see what I've done.
Pi r squared. I should have 16 pi. Sorry, this is done the perimeter first, annoyingly. I got 36.6 for the perimeter and 89.1 for the area. Because, and this is the key thing, you've got to halve this to get the radius. So the radius is 4. And then, of course, you work it out for the circle, but you've got to halve it again because it's a semicircle. So, yeah. Robert, that's it sounds like someone's drilling in the back of your laptop. But can you see where you guys made your mistakes?
I see what I've done. I've made a double mistake. I've just taken the 2 pi r squared instead of pi r squared, and I've got the r correct. But then I've made a really numpty mistake and added the 64 plus 16 pi and said that was 72 pi sort of thing.
Yeah.
So I'm trying to add A and B together and come up with C, and it's an obvious mistake actually that I was actually telling the kids yesterday not to do, and I've just gone and done it myself.
No, that's a beautiful error, because that is exactly the sort of thing that the kids do. And the reason that I threw this in is it's something that looks really basic, and you're like, okay, well, I think I can manage this. And there's so many ways that you can just make what we call these silly mistakes. But they're not silly mistakes, are they? They are just a case of, we're not being silly, we're just, there's just so many steps that you have to go through in your head that I think the kids don't appreciate. And we often also, I think I also rush and just sort of go, oh yeah, it's this, and you're looking at an 8, so you happen to write down an 8, just your brain deliberately tricking you in ways. So really clearly sort of getting them to write every step out, so sort of area of a circle equals pi r squared. So the r equals 4. I've got a semicircle, so I've got half pi r squared. And then put it in and then work it all out. Oh yes, now I've got to add on this area. And yeah, adding the pi bit and this bit together and ending up with a number of pi's. Yeah, absolutely, typical thing that the kids will do. So yes, this is something just showing you so simple and so simple to get it wrong. Through no lack of knowledge. We all know how to calculate the area of a circle and square, but just, very irritating that if you hadn't shown anything that said numbers, you might not necessarily get any marks at all. So yeah, just wanted to be aware. Nice little starter to throw in there, and then to get the kids to write their, all their answers up, and they'll be, staring at the other people's whiteboards going, how did you get that? It's obviously this. And they'll just know what's really fun. So getting them to analyse their mistakes and appreciate their mistakes is great. I mean, that obviously is how they learn. Prisms. One of those things that either seems to stick with students or they just have no idea what you're talking about. So saying that a prism is a shape, three-dimensional shape, where it has the same shape throughout, yeah, comes in any shape basically. So they have to know the knowledge about this. But then it is nice because the cross section is the only difficult bit to find. Basically, whatever the cross section is, they find the area of that. They can find the volume of their shape by multiplying that by the length. Because effectively you're saying that I've got one of these shapes this many times stuck together in order to make that. So, same for all prisms, which is nice. This is just a note on capacity. I don't see capacity, the word, come up very often. They prefer to get into things more like density and stuff, but again, these are all words they need to know. They should be used to capacity in terms of now, sort of, their phone's memory and that sort of thing. So they have an understanding that it is a sort of a quantity. And when we use it, generally enough, it's about the volume of liquid. Often they're asking that. Oh, and it's measured in litres. But when we calculate volume, it's going to be generally in centimetres. So centimetres cubed to litres, well, they need to divide by 1,000. So that's just there because I've just got a little question coming up for capacity. Yeah, it's just a way of reminding the litres are a bigger unit, so you want to make it smaller. So yeah, so the smaller numbers. So find the volumes of these two prisms, these two solids, and the capacity of this swimming pool as well. So we're doing that now. You can find the idea to find by pounds is strange. I think when I was at school we were definitely told more about the fact that centimetres cubed and millilitres are equivalent measures. So Wayne, what have you got for the volume of the first prism?
Okay, for the first one I did a half times 5 times 4 times 8 and came up with 80 centimetres cubed.
Yeah.
And then capacity, just 80 divided by 1,000, which is God, blimey. 0.0, let's just move it, 1, 2, 3, 4, 0.00, no, bear with me.
Yeah. No, that's right, 0.00.
Move the decimal point through 0.008 litres, yeah.
Yeah.
So
interestingly, so I did the same where I wrote it all out as 1, half times 4 times 5 times 8. But on the next one, I've actually found the area of the cross-section first, and then, as an extra step, multiplied it by the length to get the volume. Now, Robert, did you do it all as 1, or did you do the area of the cross-section and then multiply by the length?
Yeah, I did exactly that for both of them. Worked out the area of the end plate, so to speak,
Yeah.
and then just multiplied it all by the length. I'm usually half and half as to whether to change the meters into centimeters first to try and avoid remembering to divide by 1,000 at the end.
Oh, look, I fell right into that trap. Well done.
I kept it as meters, and then I had to remember to put 3 lots of double zeros on the end.
Oh, yes, yeah. No, I fell right into that. I thought this is much easier than I thought it was going to be. And that is because, yeah. And then, just like every student, I have not noticed that that is not centimetres. And then I've just tried to convert basically what I've actually got, which is metres cubed into centimetres. Okay. Excellent. So what did you get?
I did.
Go on, Wayne. What are you going to say?
I ended up with. Oh, sorry.
Wayne.
Sorry, I'll let Robert finish. I just did it differently in terms of working out the volume. I just did 15 times 10 times 1, and then I added half of that volume.
15 times 10 times 1, yeah. So that's just giving you that bit.
Did you get 225 meters squared out of it?
Yeah, yeah.
Yeah.
Yeah. So I did 15 times 10 times 1 to work out the area of the top rectangle.
Yeah, yeah.
And then I just divided the 150 by 2.
Because you've got a whole.
And added that.
Yeah. So that's a really interesting way of seeing it. Yeah.
Anyway.
Yeah. No, I don't really see it like that.
Same answer.
No, that's really useful to show the students, because then they can see where this trapezium area comes from, actually. And I've not really thought about this before, but also we can sort of, chop this bit off and show that we've got a square plus a triangle instead. No, rectangle plus a triangle, so not square. Good. No, well, either way is fine. But I can show you this screen. So yeah, this way I put the area of trapezium because that is how I did it. But equally, yeah, it's made up of a.
Oh, I see. I see. Yeah, I didn't even think of doing it that way. Yeah. Okay. Yeah. Just back to the
formula.
Yeah. Okay.
But that's great because you come up with a way where the students, if they don't remember the formula, they don't need to know it. There was a way to figure it out by building the solid up from the two other solids. So yes, that's good. So yes, that was the volume. I then made the mistake of not realising that was meters cubed. So as Robin was saying, yes, you've got 3 lots of 2 zeros. But yes, it's difficult to know whether to encourage the students to change it to centimetres right away, but then they've got a lot of zeros to deal with, or whether to just do it like this. Now, they are expected to be able to convert anything they're given. So technically, doing it this way, the simple way, and getting it meters, then changing it to centimetres cubed should be fairly straightforward. So they've had to effectively do what you'd have to do anyway, which is you would normally multiply each length by 100. So because there are 3 lengths, you multiply by 3 lots of 100. And then you can divide by the 1,000. So hopefully, is that what you were going to say, Robert? You got 225,000 meters.
Yeah, that's exactly what I got there. I think this one is fortunate that we're all in meters to start with. I've seen some occasionally horrible ones where instead of 1 meter there, you'll have something like 50 centimeters, and you'll have a mixture of meters and centimeters. And quite often, because we will probably do it as well, actually, given our performance this morning. We're just happy to multiply them all together, and away we go.
Yeah, and I think even if you do spot it, deciding which way you're going to convert it can just, create extra work later. But yes, you're right. Often they, especially when it's a half a meter, they like to do that one as 50 centimeters just to kind of throw you. So I think there's definitely a call for getting the students to kind of go through this, unpick it as we're doing, and identify all the different ways in which there was room for error, and sort of setting themselves up a little, well, a reasoning reminder. What are the units? Let's look at those first. What units do I need? Those sorts of things. I don't do that anymore. I think I definitely did it a lot more as a child in exams, sort of running through my list of, okay, what are the units? What do I need? And I take that for granted now, and then forget to do it. So, I think there are a lot of kids who lack common sense and really like you to do a lot of their thinking for them, as I'm sure you have discovered. And initially, they are going to want prompts that you could get them to write down. Especially a lot of, you find it, I don't know about you, but I get a lot of clingy girls. I don't know if it's just me that I attract them, but where they really sort of want me to be there the whole time, and they're like, oh, what do we need to know? What do we need to know? I need a list. I need a list I can follow. And it's very difficult to balance that. Okay, if I give them this list that they can always follow, then at least they've got that they can follow. But then their brains start to atrophy, where I'm basically not force them to have to remember this. So it's finding a balance between, yes, it's good for them to have written down that list at some point, kind of see the steps of reasoning. But what I would encourage is that you get them to draw it out themselves, that they've gone through this and they discuss on their table, what are the things that we need to notice? What is it that we should have done? Or, look, you got it all correct. What was it that you did differently to us? And to really encourage them to figure out these things so that, again, we're not just telling them, they are kind of deeply learning it themselves. So, totally other sort of, well, this is the open task scenario where you just give them a picture of something and ask them to come up with it. And actually, I've come up with a question there. What is the total capacity of the barrels in the central pile? But you could just kind of leave them with a picture and get them to make up their own questions about it, see what they can discover and tell you about the picture. And I'm wondering what I'm going to give this to you to do now, or actually just, yeah, what I want you to do is just to either start thinking about it, or just to write down your reasoning steps in order for us to see the different ways in which we think. And you could do the same for getting the kids to think about it. So trying to work out what is the total capacity of the barrels in that central pile. just start to write down some things about how you would work this out and start working it out. Does that make sense?
Got that, thanks.
Okay.
So I just have to remember to turn my mic off. I've got new neighbours next door. They're doing a lot of DIY. I didn't realise it was bouncing through the mic.
That's all right. Yeah, so have a go at doing this now.
I mean, on this one, I know we might not have finished, but in my head, I'm just following the way actually we did the last question.
Okay. So you have finished, or you haven't finished, or you just?
Yeah, no, I finished. Yes, sorry.
Oh well, no. I was going to say that's incredibly quick. I haven't really. I'm still just thinking about things. So tell me what you've done, Wayne.
I haven't actually come up with a figure. That's not what you were after, no.
No.
Oh. No.
Go on then.
So I just, from the way you and Robert did the last question,
Mm-hmm.
the trapezium area,
Mm-hmm.
and then times that by depth would give you a volume in meters cubed, and then times that by 3 lots of 100, so that will give you V times 10 to the 6
Mm-hmm.
in centimeters cubed, and then V times 10 to the 6 divided by 1,000
And
gives you back to litres.
how do you work out the size of this trapezium in the first place?
I've just done the half times bracket a plus b in a bracket times the height, and then times it all by the depth.
Yeah, sorry. So how did you get the A and the B and the H and the depth? Yeah, how do you...
What? That's what. Actually, how would you know what they are?
Yes. Yeah.
What do you mean measure? So you'd actually have to know the dimensions of a single barrel to start with, wouldn't you, and then count it. Is that what you're getting at, or?
Yeah. No, that's exactly what I'm getting at.
Okay.
Yeah.
Or get a long tape measure. Yeah.
Yeah. but that's it, Robert. What sort of thinking did you go down?
Very similar there, but I brought in estimation to a certain degree.
Yeah.
By looking at the top there and almost putting my finger across about 5 barrel widths, and then when I've got sort of 4 or 5 fingers along, estimating perhaps about 30 or 35 barrels.
Mm-hmm.
Something similar on the bottom, so I've got about 50, and then trying to do something similar for the depth of it, which would give you the volume of the construction, sort of, you know, and then just multiply that by whatever the volume of one particular barrel is.
Yeah.
So you're bringing in some sort of estimation into it as well.
Yeah.
Which would give you a rough idea, and hopefully that, certainly if you can bring estimation in for the students as well, they've got half an idea that their answer might be in the right ballpark.
Yeah.
You know, sort of instead of 100 times 2 and then they end up with an answer of 40, you can see that it's completely wrong.
Yeah. Well, I started with, yes, the single barrel, and actually started down here with this person, with thinking, okay, it looks like, I don't know, I can only say that it's a man of average height, or I have actually said let's approximate that he must be about, I don't know, 1.8 meters, and thus the height of the barrel where it's coming up to, perhaps it's, and then thinking to myself, it's probably also a standard height, is about a meter high. I have no idea about barrels. You'd think I would do, actually, because my maiden name's Salter, and that's where I come from. But, you know, the barrel I've estimated is like, yeah, a meter high. But it's, and then I've done something similar, but I have actually thought less, because I'm not convinced that it is a prism, is it? Because it narrows as it goes upwards. So I'm actually about to get into, the reason I'm showing you this is because we're about to get into truncated pyramids. But this sort of thing is really useful because the students have so much that they have to think about. You know, they have to think about how big is a barrel, yeah, how many barrels are there, what sort of shape has this created, estimating, approximating, yes, checking whether their answers make sense, and just knowing things like how tall is an average person, how tall is this house, would I expect it to be about the same height as this pile, all of those things, and then just like, and what do they, you know, if we do work it out as a whole shape, we are ignoring these tiny little gaps in between. You know, do we want to include those, or is that why our answer is slightly up? Then you could lead them into, you know, how many people could this, if this was drinking water, how much water could it, how long could it sustain people, or something, I don't know. But there's lots of questions from a single image, which would be quite nice. But yes, moving on to pyramids, because if we imagine cutting this square-based pyramid, we create, I think, a similar shape to this, because if they were to keep stacking them all the way up, it would eventually make possibly a pyramid. I mean, it is possible that it is just a trapezium. It's difficult to tell whether this is flat or sloping. And it wouldn't matter. You'd probably get some students doing it as a trapezium prism, and other students doing it as truncated pyramids, and it'd be interesting to see how similar or different their answers were. But getting on to pyramids, we used to use the word tetrahedron when I was at school quite a lot, but now I never use it. I just say a triangular pyramid. Bizarrely, I don't know whether the name is just an afterthought, or again we just dumbed down at some point and didn't even realise.
Wasn't that the shape of the old milk cartons that they used to get at school, was in tetrahedron shape?
Were they? I don't remember.
I think it was. I'm going back quite a bit though, but I thought that was the shape our milk cartons come in, and you'd put the straw in one of the apexes.
One of the corners.
Whereas nowadays you don't see them very often.
No, when I was Thatcher, I had little milk bottles. They were tiny little milk bottles we had our milk in, and we shoved a straw through the top.
Yeah.
So no, I don't remember.
In fact, even nowadays, Jubblies, little small ice packs, little fruit cartons, and stick them in the freezer. Jubbly packs will come in tetrahedron shapes as well.
Yeah.
I know that because my son still has them, even though he's 20.
Yeah, well, I do. at the rate that I'm going with my son, who's going to be drinking it out of a bottle at 16 still, I really know. I'm just right, so the volume of a pyramid is a third of the area of the base times the height. And I haven't gone into this today, but there are proofs that you can get the kids to do where, again, they discover that by kind of putting three pyramids together to make a prism that is a prism of the base. It then fit three of them in. So a rectangular prism, and they shove three of those in, so a square, basically. But I haven't done this today. But if we slice them at whatever point, we get, of course, exactly the same shape as the base. So the area then of this the volume of this smaller one, obviously just takes into account the area of that smaller base. And that can help us because if we are asked to find this truncated bit that's left at the bottom, we can find the whole volume of the whole pyramid, the volume of the smaller pyramid, and take them away from each other. And the same surface area. Now, moving on to cones. The volume of a cone is very similar to a pyramid in that it's a third of the area of the base times the height, or a third pi r squared because a cone has a round base. And the height is always the perpendicular height. Again, another thing that they forget, especially because when we come to surface area, we start using the curved surface of the cone, just to confuse everyone. Now, this formula is still given on the formula sheet. And so that's a really useful one for getting them to remind themselves of what a volume of a pyramid is as well, because you basically say, look, it's the same. The pyramid just happens to have a square base or a triangular base. A cone is just a type of pyramid with a circular base. Here, in fact, this is the formulae that they are being given on the GCSE papers. So, curved surface area of a cone, pi r L, and it does say, get them to check, highlight this, L is the slant height of the cone, H is the perpendicular height of the cone. So they're given the curved surface area of the cone and the volume of the cone, and the surface area of the sphere and the volume of the sphere, and those are the only four formulae that they're given for geometry. Everything else has to be memorised, like the trapezium and everything else has to be memorised. Although these don't need to be memorised, they obviously need to know how to use them. And one of the things we do find is that the problem is the ones that are given on the formula sheet, they then don't, because they don't have to learn them off by heart. They don't kind of have the depth of understanding. They forget how to use it, and they get into the exam. And despite the fact that it clearly to me says what the R, the L, and the H is, the kids for some reason don't read this or don't really understand, and they don't know ultimately how to use these formulae. So that's very important in terms of getting them to derive them and use them. When we slice through the cone, the bit that we're left with, this bit, is called the frustrum. And I do like to ask questions about that. But I'm happy to calculate lots of things to do with cones and slice them off. Anyway, one of the ways of getting them to derive the curved surface area of the cone formula is if you get them to open it out. And this is a really nice one to actually get them to do. So you get them to make a cone, or you've made cones, and you get them to unfurl them by cutting them up. If you can buy cones, it would be easier. But depends I know they do have these. You know, do you remember in science lessons, if you think about it the other way up, we used to have these little cone-shaped things that we used to put in to pour liquid through to filter it. But I can't remember whether we actually made the cones ourselves from the filter paper or whether you could buy cones. But either way, it's quite a nice one to get them to cut it so that it opens up. Alternatively, you could just think about getting them to say, look, construct a cone yourself. Here's a circle, give them a circle. And then hopefully they would realise they'd need to cut a wedge in it. And that wedge would be the same as their length, L. So their radius, and yeah, and so rather than starting with a cone and getting them to expand it, that you just give them a circle and say make a cone, and then tell me the surface area of your cone and stuff. And so they'll have cut a different radius probably to each other and come up with different shaped cones. So that way it'll be more interesting. They come up with different ones. So they'll measure their radius and realise that is that's the slanting side of their cone. And the circumference, because as they close this bit together, that forms the circumference of their cone's base. And so this is called the arc length. Round the sector arc length is the circumference. Now we know the circumference of a circle is pi d, or more useful is to use r. So we're going to change the d to be 2r. So we now know that our circle base has now become our arc length. How do you find the formula for the area of a sector and the area of an arc length? If we imagine that we've got an angle theta, do you know how to do that?
Not off the top of my head. No, not off the top of my head.
Okay. Robert, do you know?
The area of the sector, is that not going to be a fraction of the area of the whole circle?
It is, exactly. Yeah. So you can...
If an obvious one is a half a circle, then that would be half of the area.
Yeah.
Here you would be taking a percentage of the 360 or the 2 pi or whatever we use.
Yeah. We'll use 360. I don't think it matters in this case because they end up... So, yeah, this as a percentage of a circle is the angle theta, we'll call this bit here. Whatever that angle is, and obviously if you were doing this for real, you could get the students to actually measure it as well. So that would be nice to involve some actual measurement. So your theta divided by 360 is you're basically saying that it's a fraction of the circle. So that gives you the fraction of the circle. So in terms of area of the sector, it's a fraction of the area of the circle. So it'll be times pi r squared. However, in this case, our r, our radius, is in fact L. So we could say that the area of this sector is theta over 360 multiplied by pi L squared. Now what we also know is that the same is true of the circumference. So the circumference all the way round would be 2 pi r, which is a bit confusing because of course we've already got that here. But our r in fact is L. So our whole circumference would really be 2 pi L. And so just to have part of it, the fraction that we have of it is just going to be theta over 360 multiplied by 2 pi L. Now, of course, we know this, but we also know that the arc length, as we've said, is actually 2 pi r because it is the same as its base. So we can make those two equal to each other. And if we now cancel some of these things away, we can see that the fraction of the circle is actually R divided by L. Or, more usefully, what we can do is use that in here to say, okay, this fraction of the circle, the theta over 360, we didn't really need because we can replace it with R over L into our area formula. So our area formula now becomes R over L times pi L squared. I can cancel it out, and I'm left with the area of this whole sector is pi R L. And this whole sector is this curved surface area. And thus this curved surface area of a cone is pi R L. Very dry when I talk to you about it over a webinar, I'm afraid. But if you've given them a circle, got them to cut out a wedge themselves and made their own cone and measure all of this, then hopefully you could scaffold it in such a way that it would lead them towards discovering this formula. So, as just a bit of fun for you, 10 to 11, just thinking, do we break and then do this? No, we'll do this and then we'll break. So, as we were just talking about, the volume of the cone is 1/3 pi r squared h. So we weren't talking about that, we were talking about the curved surface area. But I can tell you that the volume of a cone is 1/3 of the area of the base, which is pi r squared, multiplied by the vertical level of the height, the altitude. And the volume of a sphere, I'm hoping it's going to tell me the next click and not go on, but it might not. Okay. The volume of the sphere is what you're trying to find in this question, the radius of this sphere, given that they have the same volume. But obviously what would be useful is if you know the volume of the sphere. Now I always struggle to remember this one because it's 4/3 pi r squared, no, 4/3 pi r cubed. I'm going to have to go back to this formula. So 4/3 pi r cubed, yes. I know it's, I always remember that one, but it's 4/3 pi r cubed. So I want you to have a go at doing this now. There's the volume of the cone. I will write in the volume of a sphere. And then if you have to go at doing this, then I'll break it after. So put your hand at the good. Right. Robert, what did you get for the radius of the sphere? Do you need to unmute yourself?
Sorry, I forgot about that. I've got 1 centimetre there.
Oh, what have I done wrong? Okay, talk me through what you did.
Right. The two volumes are the same, so
Yeah.
both those formula equal one another.
Mm-hmm.
And then it would be simple of cancelling out likes on both sides, so the third pi r squared will go. I've ended up with 4r equals h, and the radius equals h divided by 4. The height being 4, I've got 4 divided by 4 equals 1.
Four. So you ended up with 4r cubed, which was r squared h, did you? And then did you cancel? Yeah, so you cancel the r.
Yeah,
So
cancel
h over
quite a
r.
lot from
Yeah.
both sides. I end up with 4r equals h.
Yeah.
The height is 4, so 4r equals 4. R has to be 1, is my thinking on that.
Oh, I see. That is true, the thinking, but I think where it falls down is whether...
I got the cube root of 9.
Me too. Me too.
I think I've seen what I've done in the fact that both R's are not the same, are they?
That's what I'm thinking, is that you've got a capital
Yes.
R and a little r, and so we can't actually cancel through by that. Yeah, that is exactly right. So it seems very clever, and not like that.
I thought it was too easy.
Yeah, it seems very simplistic, yes. Whereas you do actually need to calculate. So you're fine to make them equal to each other initially, and then do what you did, but you just end up with capital R squared h over r cubed, and so you just have to do it that way. Or r cubed is that divided by 4, basically. Whereas I worked out the volume of the cube, I left it as pi because the pi's do cancel. So then 12 pi is the 4/3 pi r cubed. So because they're equal, we cancel the pi's, the 12 becomes a 9, and we've got the cube root of 9. That's very interesting. So good. Should be.
Yes, properly, and I've got it right this time.
Well, and I think the way that you did it, it's very unlikely actually that many students would do it that way. So luckily they would because their tendency is, you know, to steer away from the generic and to move towards putting specific numbers in. They'd probably sort of go down through this. But as you can see, this sort of question, which is, you know, very much just GCSE level, has got a lot of algebraic manipulation in it. So you're absolutely right, as we were saying earlier, you know, we're doing the algebra first. To get to be able to do this level of geometry, you would need to be highly competent in manipulating formulae, which is something the students really struggle with. You know, just where we can very simply just go, oh yeah, just cross out these pi's and move on. They really find it difficult, some of them, to know why or how they're allowed to do that. So food for thought.
That is actually that's one thing I've actually really noticed, and it's quite shocked me, is just the manipulating, moving one number side or cancelling it out. It's seems very difficult for a lot of students.
Yes, and it's difficult, isn't it, as a teacher, when you've never, because I have never experienced finding that difficult. You know, you struggle with it, don't you? I found myself initially just being like, just move it to the other side, and they'd be like, what does that mean? Because they've been taught things like, you must do the same to both sides, and they don't appreciate that that means the same as when I just say, well, just move it to the other side, because obviously what I'm technically doing is cancelling on one side at the same time as adding it to the other side, doing it all in one motion. And you lose them, and I'm afraid it's a bit of a disappointing part of the job that I do spend a lot of time just having them struggle with this, and so many kids struggle with this basic manipulation. Sorry, Robert, could you just mute yourself? Or did you want to say something?
Sorry, yeah.
Or did you want to...
No.
They really struggle with this. You're absolutely right. I think that was the thing that I was most shocked with, because we used to spend, well, we spend so much lesson time struggling through questions because their algebraic manipulation is just so poor, and their depth of comprehension about things that are the same, and they get really worried about them. So yeah, if I can recommend anything, to avoid doing that, it's difficult though, isn't it? Because how much time do you spend on something that is so fundamental when a lot of the class will have got it and will wonder why they're going on and on about it. But if they don't get it, then yeah, they struggle, and they'll never be able to do A-level. I mean, I still get some who do A-level even though they lack that basic comprehension, and well, unfortunately don't do very well. Because it just makes everything, it slows everything down, makes it very so, just before we have a break, just to say, lots of getting the students to cut out nets of shapes and, you know, sticking things together and filling things with water, if they're stuck very well, hopefully. And I've uploaded some resources. There's a Create resource which has got lots of ideas, and you can use food to get them to explore surface area. And there's quite a good one where you can get them to peel an orange, so they're working out the curved surface area of a sphere. And if you get them to peel it really carefully and lay out all their pieces and arrange them into something that they do know, like, you know, a square, a rectangle, they can work out the surface area of it. That's quite a good one. And yes, I would suggest you go into your public school and see what is in there. So let's take a break now for 10 minutes, or 10 minutes until 11:10. Have a cup of tea or something, and see you back here at 10 past 11. Is that right?
Okay, we'll do, Sarah.
Okay,
Thank you.
see you at 11:10.
Okay, see you then.
Thanks, see you.
If you're back, just say you're back. Nope, that hand up, say you're back.
Yeah, I'm back.
So Robert, that's you back as well, is it?
Yep, that counts, thank you.
Okay, so the rest of the webinar was a little bit more dimensions and there's some vectors. Dimensions, I think most of the kids, well, difficult. It's the same problem as like, seeing how many of them struggle with the algebraic manipulation. It's the same sort of reasoning skills, I think, probably. But, when we look at a formula and there aren't enough dimensions to it, we know that whether we've got it wrong or not. So volume should have cubed, area should have squared, and a perimeter or circumference will just have a single length. So just centimetres or metres, for example. So we know that if you've got something involving r squared of an area, so something like centimetre squared, L and the W, two variables, so we're not going to have a perimeter, it's more likely to be sense of area. The students are given questions in the GCSE paper which just gives them some different formulae and they're asked, what could this calculate? Is it an area, volume or length? They struggle, things like pi, letters that we use as numbers do catch them out. So it's just them being aware that when they're looking at a pi, it is not a letter, it is a number. So have a look at the following, as it says, the letters except for pi with length. Have a look at the following 6 of these and decide whether they represent a length, an area, a volume, or none of those. Right, so I'll just go down between you, each doing 1 and 2. Robert, do 1.
Yeah, the x squared, I've got no particular
Nothing in particular?
length. No, the x really, as in Dr. X or Mr. X, it could be absolutely anything at all, whatever is the subject.
All right, but if it were a formula, this is a bit weird, isn't it? It's an expression, obviously there is not a formula. But as an expression, so it's a length multiplied by itself, what would
In
it
that
represent?
sense, it would be an area of a square.
Yeah. So they're only expected to say whether they think, they don't have to say specifically what it is, but they're only expected to say whether it is a length, an area, a volume, or none.
Right,
so yeah, that is an area given a length multiplied by itself. So Wayne, what about number 2?
Yeah, I'd say that's an area length trying to be a centimetre squared or something like that.
Yeah, so that's an area. And Robert, number 3.
I think I've gone for an area there. Probably something circular because it involves pi.
Yes, that is the surface area of a cylinder, I think. 2 pi r, because that's the circumference of, if you think of a circumference of a circle, and then you roll it out. So yes, if you think about a label around a tin, is that right for that? 2 pi r? Right?
Yeah, that sounds right.
Times, yeah, because you roll out the circumference of the circle. I know this is like a heart, but if this was the wrap around the tin, in fact, right. So the 2 pi r is that circumference, and then that's the height, and that gives you the area of the outside of a cylinder, just an open cylinder. So yes, that's area. Number 4, who am I on? Wayne?
It's a volume because it's cubed.
Mm-hmm.
And I think that's the volume of a sphere formula. But
yeah. Good. Now, Robert, what about number 5?
5, I've got an area as well.
Yeah.
The first one's obviously area of a circle, and there's an add-on to it as well, which is, it's in there somewhere, but it's not springing to mind what it is.
It is in fact the same. That's 2 pi RH.
Yeah, 2 pi RH.
Yeah. So it's, again, it's the surface area of a cylinder, and the cylinder is a good one to do actually with unrolling the outside of cans, or just getting a cylinder and unrolling it, because then you get a nice rectangle, but with the top length is basically 2 pi r. Now, Wayne, what about this last one?
yeah, it doesn't look right to me. Obviously, you're trying to add an area to a length, so that's not going to work in terms of units.
Yeah. Adding two areas is fine.
You can't do it.
You can't do that one. No, so that's not good. So yeah, it's a bit of a weird question, but that is one of the things they're expected to know how to do. Right. Robert, could you mute yourself again, please?
Yeah, just going there.
Bearings. So, well, I'm sure you won't be surprised, but students struggle with all sorts of things to do with bearings. Just things, understanding what north is, and that when we write north on in a maths question in particular, but generally we talk about a north that points vertically upwards, and well, so that's the first issue with bearings really, and that the angle is measured from north. I think that's the key thing, is that they're very obsessed with wanting to do things on a horizontal basis. They don't seem to like doing it from a vertical for some bizarre reason. And clockwise, which shouldn't be too hard. That, you think that would be more natural. They often forget the 3 digits, so that if it's 72 degrees, it should be 072. So there's just some drawing out. That's really sort of all I had to say. Apart from, so just drawing the initial bearing, they struggle with. You may not have discovered this yet, but actually just using protractors, they struggle with. So what you do find is that even if they do draw their north, they then still put their protractor on it, with the protractor going, I don't have a flat protractor, I've only got round protractors as it is, so it's not particularly useful. But if this were a semicircular one, they'd still sit it like that way and have the 90 pointing up towards the north, rather than turning it so that it was sideways and measuring round from the 0. So but the way that we talk about it, we say the bearing of A from B. So we use quite, it's not really very complex, is it? But you know, their mathematicians are not brilliant. So the bearing of A from B, the key thing you have to sort of get them to say, yeah, but it's from where? Where am I looking? From B. Look at round B. They get very confused about what this language means. And then in order to be able to do all of this, they need to be able to know the angle facts and identify parallel lines and stuff. Now there's, I think I've uploaded the battleships worksheet where they just have to basically guess each other's angles and bearings and do it that way. Or there's this that is quite good, where you could just do it as a nice starter before you get started bearings. And if it's a computer game, I won't press on it now because when I do, I don't know if it will work. Let me see, it might do. Don't always project quite right when I open them. So, but anyway, this little game is quite useful getting them to discover things, especially sort of the measurement from north, so that they can they have to. So what they have to do is save this little boy over here, and their ship's here. So you might sort of say, okay, I want to get to this boy here. What am I going to do? And if they've only done angles and not done bearings, then they might think, okay, I want to turn my ship by, I don't know, 45 degrees this way. I know I'm going to hit that. But they might think that. So they type in 45 degrees, for example, and discover that their ship goes that way. And now actually, in terms of making it around the iceberg, that was quite useful. But for discovery, they'll be like, well, hang on, I want to go 45 degrees that way. How do I tell it which way I want to go? How am I going to turn the ship around to now go that way? And hopefully, with a bit of playing around, some bright spark might sorry, I'm just trying to figure out where I actually want to go. I think I might actually. Right, let me see. Yay. Okay. So it's a bit annoying the way that the program works because I kind of would like to see it turn the ship all the way around to show it's sort of doing the angle. But I think this works. It's a bit annoying that it doesn't actually go very far, so they then have to do that same thing again. But it's quite a nice one for getting them to discover how to do it. So you can either do it as a class and get them shouting it out, or each one comes up and tries one. If you've got, especially if you've got an interactive whiteboard, you can pick on those easily. But it was just quite a nice one. And this is just an example of bearings of A from B if I've been given, if I know the bearing of A from B, get them to draw their norths in so they can spot their parallel lines. You'll be amazed, well, no, maybe not yet, but the number of students who think that they can take shortcuts and that putting in a north, I don't know, takes an excessively long time. So they then don't. And then they can't see the parallel lines and they're wondering why they can't, and they're trying to figure out this angle all the way down. But from the original line. And just generally, you know, they again have to have really solid angle facts before they can get onto. So, vectors was what I was going to finish today's webinar with. There's quite a bit on it. They may be given vectors in a number of different ways. It says describe translations as two-dimensional vectors. So that It's just a case of having a vector vision like this. And just all of that, wrapped up in all of that is so much. You know, they need to understand the notation. The top bit is talking about horizontal movement. The bottom bit is talking about vertical movement. So this would be to move whatever you've got 2 to the right and 3 upwards. They like to put fraction lines in it. I don't mind if they want to use square or round brackets. But yeah, they can find that useful. But often they're just given vectors, which have just been given a letter that describes the vector. It's not necessarily into 2 dimensions. It's just the name of it. And they have to be able to, this is in the new curriculum, use vectors to construct geometric arguments and proofs, which seems very advanced for GCSE, but isn't really. I mean, they're just being asked to show normally that one thing is equal to some particular level. But there is a little notation and vocabulary and just general concepts that the students find tricky. It's very dry, vectors. I would be interested if you know any, but I struggle to find an interactive or very relatable way of teaching this, and I tend to just teach it as it is. Trying to link together the fact that there are multiple representations for the same thing, so it might be a letter and a sort of translation trick. So, just before we get into all of that, in terms of what is a vector, a distance is a scalar quantity. Lengths are scalar quantities. They just exist as measurements. So they're just a size, but there's no direction. Vectors, however, have size and direction. And I don't know if you've seen the film Despicable Me, but my daughter knows what a vector is because the baddie in that is called Vector. Because he does, I can't remember what his catchphrase is, but it's something like, I commit crimes with magnitude and direction, which is quite a nice, funny little clip that the kids might have seen to show them what vectors are. So, if you are told that ship B is a certain distance away, so a scalar quantity, but on a bearing of 50 degrees, so it's in a particular direction, then you've got a vector. And we show the size by the length of the line. Now, not if you just asked to do a sketch, but generally we do. And the direction is shown by an arrow at the end. So we can write this vector by using the endpoints to describe it. And we put an arrow over the top. So this is the vector AB. So just looking at these, which of these are scalars and which are vectors? Start the other way around. So Wayne, you tell me the first one.
Okay, that's a scalar, which is just one-dimensional.
It is, yeah, it's just a number. Robert, the second one?
I've got that as a vector because you've got a direction due south and also a distance.
Yeah. Wayne, the third one?
Yeah, it's scalar again. It's just a number, isn't it?
Robert, the fourth one?
I've got that as a scalar. I'm not sure whether I'm going to get confused with the hour on the end. It has got a distance, but there's no actual direction.
Yes, and I think it's something.
Count time as a direction.
yeah, I think that is it. The kids would be a bit like, oh, kilometres per hour. I'm kind of like, you know, like just picturing themselves travelling along a road and thus thinking that it is a vector, but it is just a scalar. Wayne, the fifth one.
Vector?
Yeah.
I'm thinking.
Yeah,
but it's not a specific distance, is it?
No, but we are travelling at a certain magnitude.
Yeah,
so,
okay.
Yeah, so that is a vector. So yes, you're right, that is the vector. And Robert, number 6.
I think again, similar like number 4, it could be confusing. It's certainly got a distance, but there's no specific direction. It's just got
I think
horizontally. If you've got a reference, perhaps yes.
I think it probably would be considered a vector. I suppose from if you think of it from the starting point, you're going to go horizontally. You have direction. You know which direction you're going. But you're right. It doesn't really have quite enough information.
Would it have to say a specific direction? Something it doesn't say, for example, left or right or forward and back. It just says
horizontally. Yeah, I know that is a bit. Oh, that's my camera, isn't it? That is a bit of a weird one. And number 7 is a vector. I would just go and. Oh no, you're right. So that isn't actually, you're right, because it's not saying left or right, is it? I am going to just leave you to read this slide, I'm afraid, and just let my cover in.
How you doing, Robert? Is everything going well?
Yeah, not too bad, mate. It's utterly confused over the last few weeks, really. But I think I'm coming up for gulps of air now.
Yeah, it sounds the same as me then. Yeah, it's so much to take in. Yeah, I'm just really scratching the surface, to be honest. But
have you done much teaching?
Not to. No, I've just been observing. So yeah, I haven't had that pressure, but yeah.
Well, I've got two schools direct actually in the same department in maths as well, so they've already started, obviously, because they've only got a year. But yeah, they started me only last week actually with 2 starters, which was quite nice.
Oh, good.
And then yesterday with a full lesson, which I must admit, yeah, definitely a bit nerve-wracking walking in. But and it was a year 10, and they're a troublesome lot. But he said, I've got my behaviour down without any problem, so that's good. That's the big worry, isn't it?
Yeah, because well, where I am, the behaviour, yeah, it's just atrocious. Yeah, it's.
Yeah, I've got
quite. Yeah, it sounds like the same type of place then. Yeah, I mean, I've been in quite a few lessons, and actually nothing has been done because, yeah, they just can't get over the behaviour. It's can't move on from it. Anyway.
No,
I've got an inner city school. Got an inner city school right next to the dockyard, so you can imagine what that's like.
What were you saying, Wayne? Are you finding it all a bit of a shock?
Yeah, we were just generally chatting and that, and I think by the sounds of it, we've got similar schools in terms of behaviour, and I've not been let loose yet. I'm just observing, but yeah, I've been in some lessons, and basically almost nothing has been done in the whole lesson because the teacher is just continually trying to sort out the behaviour or get some semblance of normality, so something can be learned. It's quite shocking, really.
Yeah.
But anyway.
No, and I'm afraid that what ends up happening is that, in order to keep bums on seats, teachers then have to fall back on the traditional style of teaching, where you just stand at the front in order to maintain the control and get them all sat in rows, and you just talk at them. And you know, you think that teaching should have moved on 50 years ago, but ultimately it hasn't because of this issue with behaviour all the time. And well, all I can say is that if the kids are really interested and engaged and you do fun things by doing really different things, then eventually actually the behaviour will settle down. But obviously, it's so difficult, isn't it, when it's kind of inherent throughout the whole school, and for you to do something else which could be obviously completely disastrous. Well, now is the time in your careers to, well, in fact, it's always the time to just play around with it. Because when you've got that sort of situation where the kids aren't learning anyway, you may as well just try something absolutely crazy. Sorry, Robert, can you just mute your...
Oh, yeah, sorry.
I've got a friend who's teaching maths at a PRU. Well, or similar. It's sort of a similar. It's a unit where basically people are sent off, they're expelled, and she just gets them, like, you know, if they want to lie on the floor and do some work, as long as they're learning, she's not bothered, and just trying to find things to inspire them and open-ended problems that gets them talking, and that sort of thing is better. She does still call it a good day if she doesn't get hit in the day, so that's slightly extreme, but yeah, it's a tough one. Going back to vectors, I'm just running through kind of the key things that you need to know about vectors and how we define them. So we say that two vectors are equal if they are parallel and the same size. So they basically have the same direction and the same size, but they're not necessarily in the same position. So DC, which is the arrow over it, is going to be the same as AB. And we've written them that way around very specifically because that is the direction of the arrow. Now, we've talked about writing them so that we talk about the endpoints, A to B, with the arrow over. We could also describe it numerically using column vectors, and that's what I was talking about before. So to get from A to B, we'd go 3 along and 4 up. Sorry, hang on, I'm just going to open the door because I think sorry, our front door locks itself on position. So 4 along, no, I can count, 3 along goes at the top and 4 up goes at the bottom. So that's it written as a column vector. That's A to B. And equally, we go B to A, but when we're going right, that's positive. When we're going up, that's positive. If we go left or down, those are both negative. So going from B to A would then be -3, -4. So we've talked about these two different ways of writing vectors. There is also, you can just call it a little letter. But I'm not going to get that one. So what I want you to do is to write down all the column vectors describing each of these. So you've got A to B, B to C, and A to C. So write down the column vectors for those 3 vectors, please.
Sorry, AB, AC, and BC.
Yeah.
The first letter.
So use the grid to write down the column vectors. So how much you've gone along and how much you've gone up. So right is positive, left is negative. Okay, Wayne, what did you get for AB?
Okay, for AB, I've got positive 4 and underneath positive 2.
Yeah. And Robert, what did you get for BC?
BC I've got -4, 5.
Yep. And then hopefully for AC, you'll have got 0, 7. Can you spot a relationship between AB, BC, and AC? So those are the vectors we found. We're just putting the arrows on them. If I think about adding these two together as if, well, as if they were numbers because they are numbers. 4 minus 4 gives me 0, and 2 plus 5 gives me 7. So AB plus BC gives me AC, and that's because when we add vectors, what we are technically doing is lying them end to end like this. So we're going along, and when we add BC, we then go along BC, and it gives us the whole vector AC. So that is a really useful fact to know, that in order to get from one place to another, if you can use 2 other vectors that you know, that will tell you the same as the whole vector. So here's a whole load for you to do. So there's write down the column vectors for A to B and B to C, and then it says add those together, and ask which one you found. And then it says copy the diagram, mark on the point E, so that AE equals CD. So it's saying so the vector AE is equal to the vector CD. So have a go at doing that now. So have you guys finished? Yeah, Robert. So what did you get for AB and BC?
AB I've got -4, 1, and BC is 2, 3.
Yeah. So Wayne, have you found AB plus BC?
Yeah, AB plus BC is equal to -2 over 4 underneath anyway. -2,
Yeah,
4.
-2, 4.
Which is equal to AC, yeah.
Yeah, exactly. And it's easy for me to say rather than easy to say it. So in order to copy it and mark on the point E, in order for it to be equal to this one, it must be the same length. That's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 in the same direction. E must be there, in fact. I click through. Good. Any questions about this?
Oh, quite happy with that, thanks, Sarah.
Okay. So, what I was going to say before, which I thought...
Yeah, oh, so...
Yeah. Go on, wait, what we say?
Yeah, no, I'm quite happy with it, but this is kind of, I haven't done this for years, so, but no, quite happy with it at the moment, thanks.
Yeah. So, often they write a vector just as a single letter. And it's underlined because basically it should be emboldened, but because you can't really embolden something yourself, we do a little underline. So in textbooks, they'll find that the letters are in bold, but when they write them, if it's a single letter, they're expected to put the underline themselves. I get a lot of arguments with students going, I can make it bold myself. Look, I'll just go over it loads of times to make it dark. I don't care. Basically, we underline it. In a textbook, it can be bold, but the person has to underline it. So this is 1, 2, 3, 1, 2, 3, 4, 3 minus 4. And that's just a bit saying it's time to bold and not to underline. Now, when it's written as single letters, it's often wanting them to end up proving things to do it. But it isn't very different to when it's just written A, B. So write down the column vectors for A and B. What do you notice about these vectors? So what is the column vector for A?
Oh. 6, 3.
Yeah. And B?
2, 1.
Yeah. What do you notice about these two vectors? And what do you think that might mean?
The same gradient.
Sorry? Robert, who's that?
Yeah, they've got the same gradient, but I don't know if that's... Yeah, I mean 6 divided by 3 is 2 and 2 divided by 1 is 2.
Yeah. So, Robert, were you going to say something?
Just, yeah, saying the same as Wayne there. The direction is the same, but it's the magnitude, isn't it, that's different.
Yeah. And the magnitude is a multiple of the other one. So they are parallel. So if you have a vector that is a multiple of another one, then you will know that they'll be parallel to each other, and that this one just happens to be longer. So this one is, 3 times as long as the original one. So...
Say that again, Sarah. Sarah, can you say it again? You just broke up there, sorry.
Yeah, so A and B are parallel, and the vector A is a multiple of vector B. So when they are parallel, you'll know this because because they'll be multiples of each other. And in this case, A is 3 times as long as B. So it has the same direction, because these are basically in the same proportion, the 2 to 1 and the 6 to 3. And you're right, that describes the gradient, doesn't it? Because you go 2 along and 1 up, that is the gradient. And it just happens that with A you do that 3 times, so A is 3B. So if you see 2 that are multiples of each other, you'll know they're parallel to each other. Right. Here we are given P and R, 2 column vectors. We're asked to find 2P and minus R. I'm going to run through this with you. 2P is just saying it's a multiple of it, so it's saying multiply this by 2. And minus R, again, it's just minus 1 times R, it's just multiplying those by negative 1 or changing the signs. So 2P will just be 4 minus 2, and minus r will be 3, 2. Sorry. Now if we would sketch these, to sketch vectors, we basically just do like the columns. So if I'm going 2 along and 1 down, P basically look like this. R is going minus 3, so going down 3 and left by minus 2, so that's going to that way. So that's the R. If I'm then going to draw 2P, based on what we were just learning above, what would we expect 2P to look like?
Double.
Yeah.
Double it.
Yeah. So it will be twice the length of P, but in the same direction, so it will be parallel to it. I'm not sure why I'm doing them, because they're written on the next slide. What about minus R? What do you think happens?
That one's just going to be the same size as R, but it's going to be in the opposite direction. It's going to be going up the way instead of down.
Yeah, and they shouldn't be curved. Let me go on to the next slide where they actually are. It'll be much better. Yeah, so 2P is twice as long and parallel, and negative R is the same length and parallel, but just in the opposite direction. So we can use those to check that 2P is definitely yes, 4 minus 2, and minus R is 3, 2. So there's just, using algebra now, what we know about algebra, where 2 times a letter, this is 2 times everything that letter represents, and in this case the letter represents a column vector. So vectors, are even stronger algebra, an even more algebraic part of sorry, all my slide bits are in the wrong place. So this is the sort of higher level GCSE questions. And often this would be the last question, and it would be one of those ones that a lot of kids look at and then completely ignore and never do. And I think maybe when teaching vectors, it's one of those things, I have done this in previous years, where I just start with this, and they don't know any of this, they don't know any of this notation, and I tell them to go and look it up in textbooks and figure out what all of this means, and they basically teach each other on the table, because otherwise it's such a dry topic. So it can be a really good one to get the kids to teach or talk about between themselves, rather than otherwise just doing what I'm doing here, where I just go, this is what this means, this is what this means, this is what this means, and it's very dry. So, can you, in terms of A and B, write down the vectors OQ and OM? Have a go first, yourselves. This was the one which I was going to show you, and then I was going to get you to do them. You have a go yourself. See how we get on. And put your hand up. So I'm going from O to Q. Think about the ways that you can get to there. But if you go the opposite way along the left-hand. So Robert, is that your hand up so that you have done this?
Yes, it is. Yeah.
Okay, so what did you get for OQ?
OQ I've got from OP to PQ, which then is A minus B.
Good, yeah. So we go along A, and then we have to do the negative of B to get to Q. Yeah. Sorry. And Wayne, to get from O to M.
Yeah, as you put, it's just half of times A minus B,
Yeah.
half of OM.
Yeah. So OM's half of OQ. Yeah. No, that's so that's half of A minus B.
Yeah, I mean, I think yeah, I can see why that's really confusing, but it's, I think, goes back a few slides when you said it's just the direction. So OQ plus QP is equal to OP, and then rearrange the equation. That's the way I did it.
Yeah, and I think the students, you know, they'd spend a lot more time possibly doing, okay, that's R, that's minus R, okay, that's B, that's minus B, getting used to doing lots more build up to this, which obviously we've not been able to do just in a short time. But this one, have a go at this one. So that we want to know AB and OP. Right, so Robert, what did you get?
AB I've got from OA to AB,
Yeah.
which is minus A plus B, or rewritten as B minus A.
Yeah. And OP, Wayne?
OP, I didn't really get as far as that, to be honest.
Oh, no, that's fine.
I'm just thinking in my head out loud.
So yeah, A to B, I go, minus A plus B, which is B minus A. I think it's quite useful to do O to P and go from O and go, okay, so you've got a couple of choices actually. You can either go OA plus AP or OB plus BP. And you'll find that students do a variety of those things. I think the easiest thing though is to think, well, if I'm going to, if I've been told AP, the most useful way is probably to go O to A and then A to P, which will be A plus 2/3 of my AB, which is 2/3 of that. That's showing the two different ways we do it. And then you just sub in that from the AB. So the A plus 2/3 B minus A, and multiply out to get a third A plus 2/3 B. Not something you'd be likely to guess from drawing that line there. But if you did get the kids to measure it, where are we going? OP. Doesn't look like it, does it? 1/3 A and 2/3 B. Oh yeah, so 1/3 to A and then 2/3 B. Okay. So that was without a third and then parallel there. So you could get them to construct it as well, just to check that they definitely agreed that that was a third along there, and then 2/3 of that. But that, I mean, that is the very sort of hardest that vectors get at GCSE. It is just, as well as being dry, it is just a bit of one of those questions that kids just, I don't know, they get, because it's quite dry, they just don't engage with it, and so they tend to leave it out. So that's your challenge, is to find it interesting to do. But have a go at doing this one. I apologise that the diagram isn't entirely accurate. But what, in fact, if we just again, Robert, what did you get for CB?
CB, I've got negative R minus S.
Yeah. And in fact, if we look at this, you see, well, in fact, if I say it's negative S, negative R, then it's just going down and across, just to go back to there. But it doesn't look quite right, does it? Because I think it should really be, and that's just if that were the case, and it doesn't quite look right. But yeah, so DB is your S minus R, DC is your 2R. So to go from C to D, you're going to have the negative of our 2R, and then add on R minus S. to get time test one as well. So it's just being able to see paths through these shapes and to not be put off. I think a lot of the students are put off by having to just call them things that aren't really real. They're not that keen on just calling them letters and living with it. That is it. Any questions about that? Or anything that we've done?
No, quite happy. I've been taught to think of them as roads or routes, and if one road is cut off, then you're trying to find a road that you know is open to get to your destination, and then you're just substituting in the vector letters and a bit of addition, and hopefully it all comes together.
Yeah. Well, and that could be nice actually, to just do it all using actual roads and stuff. That could be a way to get the kids. Not that they're really into route planning, but you know, it's something more real. There is a reason why we have vectors in life. And yeah, that is it. So Wayne, were you going to say anything? Sorry.
No, it's fine. Yeah, that was fine. I was just taking my time on CB there. I think obviously you just got to put the directions in. Once, like DC,
yeah,
you know, I'd actually draw on my diagram so I know the direction, and obviously DB, you actually draw it in the arrow.
I think I'd be inclined to
also,
a
bit clearer.
Yeah, and to have also written in here CD plus DB, and then be like, okay, well CD equals minus DC. So there's all those sort of extra steps, so that you've then got it in terms of what you had before.
That's exactly kind of what I've been doing.
Yeah, just take it step by step. And this is going to jump. Good. So if if you guys just want to talk amongst yourselves about your schools and stuff, I will come back in a second and finish up with you. Okay?
Well, how did your teaching go then, Robert?
It was okay actually. It's not too bad. I get told to perhaps rein it in a little bit. You know, in the military, you might tell somebody 3 or 4 times to sort of really nail it down. Usually once or twice in a raised eyebrow is enough in a school. You don't get sucked into an argument, which we don't get in the military.
Yeah. Yeah.
Because he did say there will be one person in the class there just sitting there waiting for an excuse, looking for that little snippet where the teacher is starting to get irritated, and then they'll just join in and all hell breaks loose then.
Yeah, that's we get kids just walking out of the classroom for because they want to. It doesn't matter what you say. It just doesn't matter what you say to them. It's just like,
no,
goodness.
It's
just all these distractions. It's like,
yeah. Some of the lives of the kids are really quite horrendous. You know, a GCSE in maths is the last thing in their mind when they've been, you know, subjected to some of the brutality they've got.
Yeah, definitely.
Oh, I just stopped the recording actually while we're